Alright, hello and welcome to a type closure screencast. Today we're going to just write a project, and I guess it's going to be something to do with compilation, analysis, evaluation, type checking, just because that's what I'm doing this semester at university. And we're going to just write a closure project and type check it at the same time. And this will be real time, and we'll see all the issues that I come across. You might learn a bit of closure, but hopefully you'll learn a bit about type closure. So I'll be using Lineagen. So what should we call our project? Let's call it typed compiler. Why not? Alright. So let's open a REPL. Put that window aside and start editing some code. Okay, well, I wanted to write an analyzer, so let's write Analyse. So let's say, what does Analyze do? Takes in an abstract syntax tree. Takes in some syntax and returns an abstract syntax tree representing that syntax. So it takes in some syntax, and let's say it returns. So it's any to an AST. I don't know. Something simple might be if it's a number, we return some representation of a node. Let's say it's a constant. Okay. And it's usually a good idea to make our projects as incrementally as possible, so we know that it's working. So let's try it out. Right, that works. Let's say if it's a symbol, it's the same. That's not right. If I'm not required. There we go. And I guess if I fall through, I want to throw an error here. Okay, well, this seems to work. So now's a good time to introduce type closure. So what I'm going to do is open my project CLJ and add a version of core.typed 7.2. And let's restart my REPL. Right, so that all works. Let's require closure core.typed and start to formalize some of these types that we have here. So we can annotate Analyse to take anything and returns some AST that we're going to define. And we can write type aliases with def alias. So we know that this AST At the moment, all it can be is a heterogeneous map that has an op key of const and a val key which is anything at the moment. So this should type check. Let's try it. Okay, so we've got no type errors. Great. I guess const is a bit of it's a big hammer. Let's say that we have a couple of different AST nodes, and then we can give slightly better types. So let's say that we can have a number operation, a number op node that is a number. And now that we have another case, we can introduce a union into our AST. Let's say a symbol node has a value of sim. I guess we could rename this, but let's just leave it as val. That makes sense. Let's type check this. Try it out. I guess if we were just wanting to double check, we could say redefine this type to say, okay, if I take in a symbol and we'll grab this, then we're going to return this AST node. Otherwise, if I take in a number, oh, I got the wrong way around. Well, okay, well, let's see if core.typed will complain. So conveniently, I got them the wrong way around. So I'm going to try and prove that if you call Analyse with a symbol, you get back a number node. If you call Analyse with a number, you get back a symbol node. Hopefully this throws a type error. Huh. It didn't. What does that mean? Sim num num. Okay. Well, let's try and trace the type checker and see where we get. Okay, so I think type closure doesn't know that number and symbol are disjoint. So let's make this a little stronger. What is going on? Alright, well, let's take out a few cases. Let's comment out this case. Alright, and let's comment out the test for it. That's still failing. And I guess comment out the default case as well. What is going on? Well, let's comment out this first arity. Let's just say if it takes a number, it returns opsim. What is going on? This is clearly not the same type as this. Alright. Something is wrong. Type mismatch. Expected HMAP mandatory. Actual nil. I really don't know what's going on. Let's add an and form. Okay. Something is not propagating correctly. Let's do a print env right here. See if we ever get to this place in the type checking. Okay, we do. And sin is a num. And there's no propositions. Well, let's just return it. Surely this will fail. Alright. That will fail. Let's try with an if. That is okay. That's baffling. How is that possibly okay? Gosh, I guess let's open up the implantation and see what's happening. Okay. So what am I going to look for? The check. When we check a do. No, even an if. I think if is the problem. Check if. Alright, well, let's abandon that project there. Let's write a test case. Right. Let's call it if expected. Here's your call to test if expected. And this is going to be a file that we can just grab this embarrassingly failing type check. Okay, that type checks. Now let's print some debugging information. So when we're type checking in if, we want to actually make sure that we've got an expected type. So this expected type is not propagating. Okay, so it's not if's fault, it's fun's fault. Okay, so here's our expected type. Fun, fun, fun. It's being checked 3 times. Oh, first 2 times any star to any. And it's just weird. Alright. Alright, so here's the check method for fun. We should always get an expected type here, I think. Checkfun, there's no expected type. And then there's an expected type here. Where is this coming from? Alright, well, def is the only other thing I can think of. Checking def. Let's say oh, okay. So all this garbage is for checking the NS form. Fine, fine. The expected for that is nil. No, this is fine, this is fine. It's just the if that's not getting propagated. So let's dig further in the check fun. Okay, so this one, check fun methods. Let's just say check fun methods expected is what? That's fine, that'll probably work. Then, let's just zoom out a bit. This is where the actual checking happens per individual method. Where's the expected type gone? Expected as a type here. We're resolving it. So the second argument is our function intersection. Fin. Now, let's debug here. No, we're still propagating it at checkFun method. So I'm expecting that this type here gets propagated as the expected type of the if. So, okay, so where does this go? Relevant functions. That's a good thing to know. Is actually matching against any of the it's really old debugging. Okay, we get a relevant function. Great, we get an expected type, which means that we're going to the second check fun one. The expected, I want to, are we losing the expected type here? No, there it is, that looks fine. So it's the range that, expected range. Yes. What is this expected range? I want to know. Expected range. that is exactly the type that I want, right? So where is it going? It's being obliterated somewhere. So this mandatory map with a symbol opsim valsim should be in this if expected. Okay, well, let's go a little deeper. Checkfun method 1. Oh. Okay. Checkfun method 1, and that is bound in the check if I remember correctly. This is just check. Gosh. Okay, so we apply check. Well, I guess let's have a little peek at what the body looks like. The body is a do. Okay, this is good. We're getting somewhere. So where's do? Check do. So this is fine. Expected type is the last argument. Expected type, propagate expected only to final expression when the increment of n is the number of expressions. Okay. I guess the smallest case is that we just go t_num and do something like if number blah, return this. Oh man, that is a bad bug. Oh, actually. Well, I assume if we just go like this. No. Huh. Why is that happening? This tool is analyzer folding. Expected num actual val a. Alright, well, let's investigate the do. Check do expected type is what? No, forgot to look. Any. Oh, that's the wrong one. Okay, well, we still got it there. That's fine. At this point, we're fine. Propagate expected type only to final expression. What is the logic here? This seems awfully... that needs to be fixed. Map indexed. Adding expected type. Okay. Whew, this is odd. That's fine. We're adding expected type num. Perfect. To what? Is what? The op expression is what? What? So we've got our expected type, check if. So if... Oh my goodness. Oh. That is just unfortunate. Check if needs an expected type. Goodness me. Expected. Oh. Always pass an expected type. Whew. Thank you very much. Goodness me. That serves me right, to be honest. I did that to flush out a lot of bugs. Rather, I relaxed the outer expressions doing double checking, and the inner expressions sometimes don't propagate expected types properly. Oh, that is just brutal. Alright, so... Alright. Let's install that. I don't think we need to build... Yeah, install jar. And we can just... I think we're up to 7.3 snapshot. Oh. Ooh. What version are we up to? What on earth was that? Oh god. Anyway, let's ignore that. What is this other POM? Is this old? Ah, Lineagen. Ugh. Auto-generated. False alarm. Alright. Let's try again. Whew. I just realized we're going to have all the debugging information, aren't we? So the only fix was this line there. Okay. Stage that. And we can obliterate the rest. So propagate expected type to if. Probably a good time to document this. Oh, anyway, how's our REPL doing? Alright, let's cross our fingers and see what happens. Wait, let's install it again. Alright, well, might as well initialize a Git repository. Let's start our REPL. Should be a little faster since we've installed the compiled version. Let's go back to which version? Yes. Excellent. And we'll type check it. Hallelujah. Alright, type mismatch, expected number. Yes, this is exactly. So if we, so at this point we're expecting val number or val symbol. So yeah, this is a limitation of attaching metadata to closure forms. So there's no way to get the line number of this form, so it'll find the nearest line number. So this is actually complaining about this number. So what this type is saying that if this is a symbol, then we're expecting a number. So we've actually got the implementation correct, but the types are wrong. So we can grab this. If we type check this, it should tell us that we've got it right. Oh, okay. Back to what I originally wanted. Excellent. That is actually working. Man. I was not expecting to fix a bug in the first 30 seconds, but it happened. Alright, so let's add what? So let's say our syntax, that is a number node, a symbol is a symbol node, let's say a list with a fun, some symbol and an expression is a fun node. So let's say if it's a list, then if the first element is a there's a fun, return an op fun. Might be easier just to, well, let's just put it in here. So the name, let's say we're only allowed one binder, so it's the second of sin and body is what? Call index is the third thing. Okay, so actually nth requires something that's sequential, so we need a better, well, let's just see what core type says. Type mismatch, expected AST actual. Okay, so we need to add fun. Let's say its name is a symbol and its body is an AST. So let's make this a recursive definition. And let's ask again. Okay, so what's this actually saying? At this point, expected AST actual is HMAP with the correct fun, bad looking name and some body, which is any. Okay, so the body clearly needs to be analyzed. Okay, so we've got that. What's this saying? The name needs to be a symbol. Okay. So let's do a bit of error checking here. Let's say we're destructuring sim. It's a bad. Let's call it name and body. And we'll destructure our sin. And we'll say analyze that and analyze the body. Okay. Expected AST. Okay, so name is still the wrong type. So what we need to do here is add some error checking. Assert that n is a symbol, otherwise say fun binder must be a symbol. Actually what we want this, don't we? Because we want it to be like a fun and then a symbol, yes. So let's forget about destructuring for now. Okay, nth could not be applied to arguments. So we're trying to destruct something that could possibly be a non-sequence. Okay, fair enough, core.typed. Let's say we assert that n is a vector. And say fun binder must be a vector. Let's say that it has to be a vector of 1 as well. Of 1 of count 1. And then we can destruct that. Okay. So fun binder must be a symbol. Great. Is this going to type check? Alright, expected AST nil. Where is this? Alright, this is this point here. So yeah, there's a base case here. We need to go well, let's blame the user. Let's say bad expression syntax and blame the user. Alright, that type checks. Alright, let's check this. So if we have fun with some expression and returns a number, it should work. Alright, we should be able to get this output and quote it and say that it is an AST node, right? Okay. Another way to do that is at the REPL, we could have call to CF, and that gives us the type, tells us that that successfully type checked. Say if we remove the name, we would get something like expected an AST, but we got something that's missing a name. Great, so we can stick that in our test there. Alright, well, what have we got? We've got 2 leaf nodes and a recursive node. Well, that's enough to do some interesting things. I guess, what could we do? I guess we could compile this to closure, and let's might as well do that. Let's write an emit function. Takes some AST and then tests on the let's say const p of the op. What is the syntax? Test expression. So that should work. Well, let's try this out. Let's use some static type assertions. Alright, so let's say emit takes an AST and returns some syntax. Actually, to make it fun, let's call our operations lambda. So this is a compiler for simple, I don't know if it's going to be typed, for lambda calculus for now. It'd be cool if we can make it a simply typed lambda calculus. Alright, what's it saying? Type mismatch any. Okay, so something's wrong. So maybe type closure isn't smart enough to figure that out. How's this? Okay. So type closure can figure that out. And because we're returning of any, type closure doesn't care about the base case, so it's not giving us an error message. So unrecognized AST node, let's say. So let's say we can analyze lambda, analyze it, emit, and then eval. Okay, that's fine. Yay, that worked. Okay, so let's do the same for symbol. Yeah, that's unreadable. How's that? Okay, cool. Type closure's fine with that. These are exactly the same. Okay, so let's say this is going to return a union of symbols and numbers and get rid of that. Cool, so I guess at this point in the program, core.typed thinks it's either a symbol or a number. Cool. Alright, we're getting somewhere. Let's add another feature. No, let's teach it about lambdas. So if we've got a lambda, what have we got? We've got a name and a body, I think, if I remember. We've got a name and a body, which is a symbol and an AST. Cool. So let's splice in our name, and just for the hell of it, let's add some static checks. Say that name is a symbol, and body is a AST. Let's make this one line. Okay, so name is a sim, body is an AST. Okay. This helps with any typos or anything like that. It can help type closure tell us. No visual bell. Cool. Okay, so we don't need to splice this, we just need to emit the body. This should be fairly straightforward. Unannotated var. Not yet implements function inference. That is weird. Alright, I guess for now, let's say name is the name. I really don't know what was going on just there. Body is the body. Oh, maybe it's this. Maybe it's syntax quote. Yeah, that's probably what it is. Let's dumb this down for core typed. Where is hashmap being called? Unannotated via hashmap. 4230. It's not being called. Unless syntax quote is calling it. Huh, so it was my sneaky and form. I think? No? Oh, just something. Something spazzed out. Alright, just for my sanity, let's just try again. Alright, same weird error. That's fine. I think that's what I had just then. Okay, and I think if I change this to a syntax quote, wow, okay. What on earth does this macro expand out to? I am so confused. How is that different? Whatever. Well, we don't need to blame the destructuring. I think that's fine. And we can make this one a little nicer, actually. So that says the same thing. Oh, okay. So now we should be able to do lambda x is that, and we can. Okay. Ah, we don't have an application rule. Let's write that. So we can. What's an application? It has an operand and a operator. Okay. So if we have a list, if the count is 2 and it's a list, then we have a an application, right? Rand Okay, that should work. Type check that. Okay, that type checks. We should be able to get as far as emission. No, as far as analysis. So let's get rid of those. Should be able to analyze that into a rand narrator. If we try and emit it, we'll get unrecognized AST node. Okay. So let's say it's an app. The op of the AST is an app. We've got a rand, a narrator. Might as well turn those around. Let's do a similar syntax, a similar destructuring check. And it's actually an AST. But these should be checked in the body anyway, because we're going to call emit inside them. Fine. So we're going to make a list of emitting the rater and then emitting the operand. So if we just run this, we should be able to get something out. Hallelujah. That works. Okay. Does this type check? Okay. So these aren't strictly needed, right? These are just checks that help us while we're programming. But I like to leave them in for now. We can always delete them later. They literally macro expand out to nil. Okay. I guess it would be nicer if we could refactor some of this into a multi-method. So say this emit multi-method is usually, emit function is usually implemented as a multi-method. Let's gradually convert it to a multi-method. Let's call it emit multi-method. It's got the same type as before. And it's going to dispatch on the op key. And let's say, instead of defaulting, let's call our default let's make this our default. So else call emit multi-method on the AST, and that will unable to emit multi-method. Okay. So let's emit, what have I, def method. Okay. So let's say we want to move the number operation to the multi-method. Def method, emit multi-method number, and that's an AST node. So this is check we don't need, we're already here. We know that we've got a number just to make sure. And we'll get rid of this case here. So if we just run it, it should all work as before. Okay, that's promising. If we type check it, okay, that works. Let's move the symbol case over here. This was just tsim. And we can get rid of this case. Great. This should just be A. Cool. We can get the lambda down there. Let's grab this whole thing. Maybe put this here. Lambda. That works at runtime. Let's check it. Okay, type closure's happy. And our last one is the application. And that is, we can def method, emit application. Okay. Does it type check? Okay, fine. Type checks. Does it run? Sure. Great. And we should be able to evaluate that. Great. Well, we don't need this function anymore, so let's rename it. Cool. Just type check it. Great. Do we want to make Analyse into a multi-method? Not really. No, that's a bit too annoying. That's fine. Cool. I guess we could turn this into a typed lambda calculus. Let's say, let's get rid of our lambda. Actually, what's the best way to do this? So I want to attach a bit of information to a lambda, like, might as well copy the type closure syntax. So now lambda is going to have a annotation. Let's say it's a type, which is just a symbol. Or it's just, let's say types are just some syntax that we make up. Might want to revisit that later on. Okay, so what do we need to change? So our vector must be a vector of 3, because we've got 3 positions in our thing. So let's add a little bit of error checking here. Lambda binder must, let's say, symbol and type. Otherwise we use this type here and chuck it here. Whoops. Oh, this will do for now. So we need a type environment. Yes. What's the best way to do that? So we could have a dynamic variable. Might as well do that. It's called a tenv. And it's a map from symbol to types. Let's just have a temporary annotation for types at the moment. Okay, so it's a map from symbols to types. So what we want to do at this point, we want to bind our tenv and associate the tenv to have a type from n to t. So when we analyze it, we know that, yes, the current local binding n in scope has type t. I don't know. What's the best way to... Should we have an expected type here? So let's say that every AST has a type. Okay, that's fine. So to calculate the type, we probably want to use our let. So the type is the type of the body. No, it's a list with T and then an arrow type of body. Right, yes, this is it. So we don't want to run our programs yet. So number constructor has type num, symbol constructor has type sim, application is slightly harder. Okay, so we want to bring out these radar rand. Okay, and we want this to be radar and rand, and the type is going to be what? So at this point we expect the type of the radar to be what? A function type from an argument to a return type. Okay. Let's call trader a type. Not that this is going to help us at the moment, but let's assert that trader is a list. Okay, well, this is getting a bit unwieldy, so let's flesh out this definition of what a type is. Let's say it's either going to be a base type that is either int or a sim. Let's call it num or a sim. Otherwise, it's a function type let's call it param. And again, we need to make this a recursive type. Param return. Great. Type. Yes, this is going to help. If we get out the if we analyze the operator and we know it's a type, it also has to be a function type. So it has to be a lambda. So let's say it has to be a param and a let. This is probably an easy way of saying it. Let's use the typed let. Okay, so let's analyze the rand and assert that the the type of the operand must equal the param type. So we're expecting param t. The actual is the inferred type. Okay. And I guess we could give a line number here. We haven't quite got. Let's forget about the line number for now. Okay, that's fine. Map literal must contain even number of forms, 76. Okay, so the type is the rater, which is what? Ret t. Lambda binder must be a vector of count 3, so now we have a typed lambda calculus. This is going to be an int. This is the sim. Assert failed. Lambda op t rater. Let's start easier. Okay, so analyzing this. So let's just comment out our failing tests. We should be able to compile, so now we can type check. Found type errors. Internal error, bad type syntax. Oh. Okay, that's fine. Okay, what do we expect? An AST got back something that's number, complete true, val, type. Okay. What's the difference between that and an AST? Ah, it's this thing, because now we're expecting a type. So where's this? 39. So now we want a base type. So let's have a helper function. Base type makes takes some symbol, returns a type. Let's say it either takes in a num or a sim. And let's abstract out this. Say base types. Fine. Takes in a base type, returns a type. Okay. So we're constructing this. Okay, we have our ad hoc thing. So we want lambda type, take in the argument and the, lambda type takes in the parameter and the return type. What is it? Lambda type takes in two types and returns a type. Lambda param ret. Okay, how's our parens? This is fine. Type ret t. What is ret t? Okay. Now let's type check it again. What is t here? So t needs to be a type. Okay, so we need a pass type as well. Lambda type. So we need to say something like pass type here. So pass type takes in some syntax and returns a type. So we should be able to say if it's a base type, then just make the base type. Otherwise, if it's a list, and let's say the second argument is what? An arrow. Cool. Then make a lambda type from first sin to the nth, and the third of sin, else. Bad type syntax. Sin. Okay. Quote here. Bad type syntax int. Okay, so does this actually do what I think it does? Oh yeah, because int isn't a base type, is it? False. True. So where's int? So it's actually num. Actually, int makes more sense here. But we're using number everywhere. Okay. So num. Okay, that seems to work. It's a lambda. Alright, let's type check this again. Okay. So nth needs something that's sequential. So let's say that it also has to be sequential, which actually isn't implied by the types. But it'd be pretty weird to have a list that wasn't sequential. But simply this predicate check isn't enough to prove that the nth call will never throw an error. Nth cannot be applied. Persistent list. Oh, this is so weird. Screw it, let's just say that it's a vector. So clearly that is never going to fail. Why? Oh, that is... Oh. Embarrassing. Alright, so... Sorry, type closure, you're right. Lambda type cannot be applied to arguments. Option any. So we need to pass this. And again, this t here needs to be passed, because the first argument is any. Let's fix some of the other ones. Yeah, that's the same error, What is this? Actual vec any. What is param t here? T rater. So my pedanticness did come in handy. So T rater is a lambda op. Any. So param t here is any. Ret t here is any. That's surprising. What is this? This is a type. So clearly this is not sufficient. This is a bad. Huh. So T-rate is a type. Oh, yeah, this is a terrible test. So, um, so we have to pass this type. What else? This conditional is the same error. Yep. Okay, so to make this correct, we need to make this a type. Lambda type base takes what? Takes an int and returns an int. That doesn't really matter, but I guess it's useful. Okay, this is actually complaining now. So this AST, I think the type is wrong. Type is list. Huh. Wait. What about this inner thing? Let's give it a better type. Base type int. Oh. This should be num. What is this even saying? This looks wrong. What is this? It's a list of base type. Where is this coming from? Oh, the body? The body is type. It's a list star of base type, quote, num. What? Well, that's clearly wrong. That should just be type. Alright, well, let's add some and forms. That might help. Say this is a type.